Hello, my name is Cole.
I'm Jordan.
And I'm Jesse, and our senior project is titled Golf Club Prototyping and Design for Spin Rate Tuning. The problem we intend to address in this project involves the difference in wedge spin rate between the average amateur golfer and professionals. The average amateur golfer generates about 7,500 RPM of backspin, while professionals generate upwards of 10,000 RPM. Increased backspin allows for shots to stop quickly on greens, providing better shot control and precision. The average amateur golfer hits about 13 pitch, chip, or sand shots with wedges per round, so an improvement to the wedge would have a huge impact. Wedges, like all other golf clubs, are governed by regulations imposed by the United States Golf Association, or the USGA. These include specifications on groove shape, club head dimensions, and face roughness, among others. Thus, there is a limited set of improvements that can be made to improve golf club performance within these regulations. In recent years, additive manufacturing has progressed as a viable alternative to traditional manufacturing processes in terms of cost and quality. Using metal additive manufacturing allows internal features to be included in designs that would be difficult to produce with traditional processes. Our literature review focused on three areas. First, we looked at existing wedge designs and determined methods that other companies use to increase backspin. This gave the problem some context and will help us as we develop potential solutions. Next, we searched for mathematical models and simulations to calculate theoretical spin rate. This will drive the analysis of our designs and help us to determine which of our alternative designs would provide the largest increase in spin rate. Finally, we reviewed previous research on applying additive manufacturing processes to improve the performance of other golf clubs. The main benefit noted from this research was the ability to redistribute weight as desired due to the porosity of additive metal structures that can be carefully controlled.
Contrary to the way that wedges are currently designed, we aim to create a sandwich mesh design within the wedge, which will allow the deformation of the face of the wedge. This will increase the impact time between the ball and the wedge, producing more spin off the face of the wedge. The first step of this design is to obtain a SOLIDWORKS model of an existing wedge, which we will produce through additive manufacturing, and use as our control for testing. Next, we will design several different meshes for the sandwich within the wedge. The meshes we design must conform to the USGA regulations, which Jesse mentioned earlier. Using finite element analysis, we will be able to predict the effect of the meshes on the spin of the golf ball. Once we produce a few prototypes, we will test the control against our redesigned wedges to determine if there is a significant increase in the spin generated. To begin our project, we wanted to make sure that additive manufacturing techniques were capable of producing the precise grooves on the face of the wedge, so we printed a small sample of the grooves in plastic. The grooves came out quite well, so we moved on to obtaining a SOLIDWORKS model of a full wedge. We reverse engineered this model by taking a digital scan of the existing wedge made by Scratch Golf. The digital scan was a little rough, but after minor repairs, we were able to print a plastic version of the model.
Some tools that will be necessary for this project include CAD tools such as SOLIDWORKS for the wedge model and design, as well as NetFab in order to repair the 3D scan. Finite element analysis used to analyze the alternative mesh structures. Product costing analysis in order to determine feasibility and pricing. And lastly, design for manufacturability, used to propose a manufacturing process able to produce large quantities of our product at low cost. While new technology such as composite materials has been widely applied to drivers, wedge design has remained relatively similar in the past few decades. Changes are generally limited to aesthetics, with some tweaking of center of gravity and moment of inertia in order to adjust ball flight. Traditionally, the short game, described as 100 yards and in, has been the most important aspect of scoring in golf, so an improvement in wedge performance would lead to lower scores for most amateur players. Incorporating groundbreaking new technology into a wedge also has the potential to provide huge economic benefit for golf club manufacturers. Cleveland Golf, a company famed for its wedges, made $36 million in revenue in 2015. The economic potential for implementing our technology, if successful, could significantly increase a company such as Cleveland's annual revenue. At this point in the design process, we have been able to produce a plastic printing of our control wedge as pictured on the right, and we are moving on to the metal printing of our control wedge next. We will then begin the design and analysis of our mesh structure using finite element analysis as our testing resource. Following that, we will begin integrating the selected mesh designs into the wedge model, and we will print the model in both plastic and metal. Lastly, we will test the new wedge prototype against the control wedge in order to determine whether we were successful in our design. Thank you for your time.